Let's start with a fascinating paradox. As AI models get better at step-by-step thinking, they face a hidden trap when reading long documents. While models like Claude and DeepSeek excel at short context reasoning, extending their thinking traces to long context settings introduces a critical failure mode. Instead of actively analyzing the text, these models begin to mindlessly copy massive blocks of text from the prompt directly into their reasoning traces. This behavior wastes precious token budgets and prevents the model from actually solving the task. To understand this problem, researchers uncovered a striking trend. Models literally copy-paste text instead of reasoning, and this issue gets worse as the input document grows. If you look at Figure 1 on page 4, you can see the n-gram overlap rate across 7 frontier models. Even at a modest 8,000 token context, models copy up to 43% of their output. By 64,000 tokens, some models spend over 70% of their thinking budget simply transcribing the prompt. This is a systemic issue affecting both open-weight and proprietary models. This copying behavior isn't just harmless filler, it actively destroys the model's ability to solve problems. Figure 2 on page 5 illustrates this damage clearly. When the overlap rate remains below 40%, the model maintains stable accuracy and reasonable thinking lengths. However, once a model crosses this threshold, its accuracy collapses to near 0%, while its thinking length triples to over 58,000 tokens. The model essentially exhausts its entire generation budget transcribing the input, leaving no room for actual problem solving. The underlying mystery here is why this happens, and the answer lies in a metric called the grounding ratio. By splitting prompts into key evidence and irrelevant distractor context, researchers measured what the models were actually copying. As shown in Figure 3 on page 6, successful models exhibit a much higher grounding ratio. They selectively copy only the critical evidence needed to solve the task. Incorrect models, on the other hand, copy indiscriminately from both key evidence and distractor text, proving that the issue is a fundamental failure of selective attention. To fix this, the authors designed a clever solution called GEAR, which reshapes how we reward AI models during reinforcement learning. Instead of relying solely on whether the final answer is correct, GEAR introduces 2 complementary n-gram overlap signals. First, a grounding reward encourages the model to engage with key evidence. Second, a distractor penalty punishes the model for copying irrelevant context. Together, these forces train the model to be highly selective, preventing it from copying everything while ensuring it still focuses on the necessary details. Of course, training GEAR requires annotated data, which is where a new 3-stage automated pipeline comes in. First, a language model analyzes a raw document to identify its informational characteristics and filter out unsuitable content. Second, the pipeline segments the document and samples a small constraint context to generate a targeted question. This guarantees we know the exact evidence region by construction. Finally, an independent model verifies the answer using only the constraint context, ensuring the generated question is clean, unambiguous, and perfectly annotated. When we look at the experimental data, the results are incredibly clear. GEAR consistently outperforms standard training. Looking at the tables on page 9, GEAR achieves up to a 4.6 average improvement over standard reinforcement learning. More importantly, these gains actually increase at longer context lengths, even though the model was only trained on shorter contexts. GEAR also successfully cuts down thinking length and overlap rates, proving that the model is learning a robust, generalizable grounding behavior rather than just memorizing shortcuts. While GEAR represents a massive leap forward, there are still a few key limitations we need to address. Currently, the automated data pipeline is restricted to single-valued answers like numbers or entities to make reward computation straightforward. Additionally, the method relies heavily on the quality of the initial document chunking. As we look to the future, extending this evidence-aware reward framework to free-form, open-ended generation will be a crucial step in unlocking truly reliable, long-context reasoning for the next generation of AI.